Welcome to Lesson 2 of the Physics 30 Prep Fast Track. In Lesson 2, we'll look at understanding graphs and relationships, formula manipulation, and using the correct units. Much of scientific study is the study of relationships between matter and energy or other variables. We study what happens to one variable, that is the dependent variable, or sometimes called the manipulated variable, when changes are made to another variable. That's called the independent, or sometimes referred to as the responding variable. So, in a particular study, we may observe that for a particular student, the grade increases as study time increases. Seems to make sense. We manipulate the study time and watch the effect on the student grade. So some students might study only for a very short period of time, and their mark might not be all that great. Whereas other students are given lots of time to study, and they might end up having a slightly higher mark. It's not always going to be that case, because of course there are other things to consider, like how effective is the student studying, or the student's study habits, how much background knowledge, what's the math skills, and so on. But in a large group, the trend would likely be a direct relationship. So this graph on the left shows a group of students who might have gotten a low mark with no study time, and as the study time increased, the mark also increased. This is called a direct relationship. Direct relationships from your math classes are often shown using the formula y is equal to mx plus b. So here's a practical application of this math concept. And of course the y is, in this case, the y is the student mark. The x is the amount of study time. So these are the two variables that are changing. The b, of course, would be what we call the y-intercept. It is the student's mark with no study time. So it doesn't have anything to do with the experiment, except for this is the sort of starting point. All right, at zero study time, the student's still capable of getting a certain mark. Not that high a mark, but a mark. Not a zero mark. Now, with some relationships, the graph starts at zero because with zero input, there is zero response. And so the mark would be zero, perhaps in some courses. You might even get a zero had you not had any knowledge of the concept at all. So the formula for this particular relationship would be y is equal to mx, because there is no value of b. You'll see these relationships, these mathematical relationships, you'll see them in a lot of your physics equations as well. All right, so this is an example of a direct relationship. Now, sometimes when we change the independent variable or manipulated variable, we don't see a direct response. We don't see, one thing gets bigger, the other gets bigger. Sometimes we'll see what is called an inverse, or perhaps even an exponential effect on the variable. So, for example, we might observe that for a particular group of students, hours spent playing video games may have a negative effect on their grades. What we're saying here is their student mark is the responding variable, the amount of video game time is the manipulated variable, and as the amount of game time increases, their mark goes down. And this is a typical example of an inverse relationship. One thing gets bigger, the other thing gets smaller, and there's lots of examples of that. When you drop an object from a high building, in the first second of travel, because the object's just left your hand, it's not moving very fast. And so in the first second, gravity accelerates it, but only to a certain speed. In the second second, it already has that initial speed from the first second of travel. It's going to accelerate to an even higher speed. So we see that in every second of travel, the object's moving faster, and therefore it must travel more of a distance. And in fact, this is an example of an exponential relationship. And an exponential relationship looks like this. So what we're saying here is that there are basically three types of relationships. The first one is a direct relationship, where as one thing gets bigger, something else gets bigger in a proportional way, in a direct way. All right? So an example here, the final velocity is affected by, of course, the initial velocity and also the acceleration and the length of time. Okay, so that's an example of direct. When you talk about two planets and the gravitational pull that they have on each other, or the attraction, this is an example of an inverse relationship. The closer the planets are, the greater the pull. The further apart the planets are, the less the amount of pull. This is called inverse. And in Einstein's famous equation, if you could change the speed of light, then as you change the speed of light, the amount of mass that an object has or the amount of energy that a mass has would be affected exponentially. So here's an example. Just the c squared shows you some kind of exponential relationship is going on in this particular case. And when you study particle accelerators and so on, you'll see that especially with relativity, these exponential and these effects are quite significant. All right? So those are exponential, inverse, and direct relationships. Now, one of the things that we do with these relationships, once we've established which one we're working with in a particular situation or experiment, is we want to take the given formula and possibly manipulate it into a new form. This is a skill that you use a lot in Physics 20 and 30. So let's take a look at how that skill starts and how you can develop it. When we observe a relationship in physics, let's say we're watching an object fall, or we're watching a car race down the road, or you're catching a ball in your catcher's mitt. These are all relationships. Now you could say, all right, an object is moving at 5 meters per second, and then it accelerates at a rate of 2.5 meters per second squared for a certain period of time. We don't know what that time is. But we do know that after we've finished accelerating, it's now moving at 20 meters per second. So that's a common situation. The formula that we would use to solve for time, and this is something that comes with practice, is knowing which formula to use, would be VF is equal to VI plus AT as shown. You know VF is 20, you know A is 2.5, and you know the initial velocity was 5. How do you solve for t? Well, on most formula sheets that accompany an exam, you might have this particular formula. All right, this is your starting formula. However, it's not solved for t. In order to solve this for t algebraically, you use the basic golden rule of math, which is whatever you do to one side of an equation, you do to the other. In order to isolate t here, we need to get rid of everything else. We need to isolate t. That means lose everything else. So how do we get rid of VF or VI? Well, we subtract VI from the right-hand side, and at the same time we subtract it from the left. Subtracting it from the right leaves a blank there. Subtracting it from the left leaves us with VF minus VI. The next step would be to isolate t, we need to divide both sides by a. So we divide one side by a and the other by a, and we end up with this result. Now once we have the result, then what we can do is take our values and plug them in, or they call it substitution. And so by substitution, since t is equal to VF minus VI over a, t is equal to 20 minus 5, final minus initial, divided by the acceleration that was taking place at that time, and we find that the time of acceleration is 8.00 seconds. And that would be the solution that we're looking for. All right, so you can see that You're given some information, you have a basic formula, manipulate that formula to help you solve for your unknown. That's a common practice in physics 20 and 30, and all through later stages of physics as well. So another example, same kind of idea. We've got lots of examples here for you. D is equal to VIT plus 1/2 AT squared. This is another standard formula that you're given a little bit later in one of the lessons in this first unit. So if you knew that the initial velocity was 20, an object's moving along at 20 meters per second, suddenly it undergoes an acceleration for a particular period of time. As this acceleration is occurring, of course, the object's moving, and we're told that it moves a distance of 500 meters or half a kilometer. So they give us the time, they give us the initial velocity, they give us the distance traveled. What we want to do is solve for A. So again, we start with our basic formula. D is equal to 1/2, or VIT plus 1/2 AT squared, and we have to solve it in this particular case for A. What is the acceleration? Golden rule of math, whatever you do to one side, you do to the other. So the first thing we'll want to do is isolate the term, all right? And the term that we want to isolate is the one containing A, since A is our unknown. So to isolate this term, we have to get rid of the VIT. So it goes over to the left and becomes negative. So D minus VIT is equal to 1/2 AT squared. Then to isolate A, we divide both sides by T squared. And we end up with D minus VIT over T squared is equal to 1/2 A. The last step is just take this right side, to get rid of the half, you multiply by 2. Oops, that's a 2. All right, and whatever you do to one side, you do to the other. So we multiply the left-hand side by 2, and we end up with 2 times D minus VIT over T squared is equal to A. Then we substitute our values from above into this algebraic solution. A is equal to 2 times D minus VIT over T squared. 500 minus 20 times 5. You'll notice that the 20 meters per second times 5 seconds gives you 100 meters. So it's 500 meters minus 100 meters, and then we divide that by 5 seconds squared. And we end up with 32 meters per second squared. That is the acceleration of the object in this particular situation. And the last step is, of course, once you've manipulated a formula, it's a good idea to check whether or not you get the right units. So in the first example that we did, VF minus VI over A is equal to T. Notice that as I work through the units here, the units of time are seconds. So we know we need to end up with seconds, or perhaps hours or minutes or whatever, but in this particular case it's going to be seconds. So how do we know that we've manipulated the formula correctly? If the units work out properly, it's a very strong indicator that we've done everything correctly. And meters per second minus meters per second, still you have meters per second. Divide that by meters per second squared. Well, dividing a meter per second by a meter per second squared, you're taking a fraction, meter per second, dividing it by another fraction in math again. One of the rules is that if you divide a fraction, it's the same as multiplying by its inverse. So a meter per second divided by a meter per second squared is the same as a meter per second times a second squared per meter. And the units cancel nicely to give us seconds. All right? Same thing with the bottom. If we have 2 times D minus VIT over T squared, the 2 has no units, but D is meters. VI is meters per second, but when we multiply that by a second, the seconds cancel. We're left with meters minus meters over second squared, or again, meters per second squared. You can see the units canceling, all right? Meters on the top cancel meters on the bottom. Seconds on the bottom are canceled partly are canceled by the seconds on the top, leaving 1 second on the top in the first example, and you can see the seconds canceling in the bottom. And there are our correct units. Correct unit for time, correct unit for acceleration. Chances are we've done it all correctly, and we'll show you a few more examples of this. There are some couple of formula manipulation flash animations that you might want to take a look at, but of course looking at it doesn't give you the expertise that doing it will give you. All right, so look at some of the examples that you're going to be asked to do in your WebCT course. Make sure you can manipulate these formulas, or definitely use the time to seek out tutorial help in this particular case. This is an important part of your set of tools you need to become successful in Physics 20 and 30. And that's it for this particular lesson.